The next slide I think you have is called latent heat. Okay. And before that, we were talking about physical phase changes, and we said actually for the top ones, you have to put energy in. So we are adding energy. They are endothermic. So actually here in a minute, we're going to have something called the latent heat. Latent heat. And it's going to be another delta H. So it's going to be the latent heat delta H of melting. Actually, we're going to call it fusion, so I don't want to confuse you. I don't know why they do that. It's going to be delta H of melting is the same thing as delta H of fusion. Don't blame me. Okay? So how much heat do you need to, if you have 3 grams of ice, how much heat do you need to add to it in order to make it 3 grams of water? That's actually your delta H of fusion will get you there. The next one, delta H of vaporization, VAP. And I hadn't thought about this till just now, but the next one, to me, if you have something that goes from, I don't think I've seen delta H's for those. I haven't seen heats of, actually I have, but we aren't going to be dealing with them. It has to be delta H of SUV. And then these actually are exothermic things. So energy is released. Okay, so energy is released. I'll just put, instead of adding E, I'll say E released. Okay, and we know that those are negative delta H's, right? So actually, these are going to be negative too, and I'll kind of tell you how they relate to those here in a minute. But that's what we're talking about when we're talking about latent heat. Latent heat is just saying it's an energy change that actually is resulting in something changing its physical phase. From a gas to a solid, or from a gas to a liquid, or a liquid to a solid, or somewhere in there. Okay, those are, so we have the latent heat of vaporization. So vaporization, evaporation, they're kind of the same verb, I guess you call those. I don't know. So it can be given in energy per mole of substance that you're taking. By the way, I'm a picture person. I think some of you guys are too. So anytime we're talking about vaporization, we're talking about something going from a liquid to a gas, right? That's what we're talking about here. So how much energy do you need to zap for your liquid, if it's in terms of moles, to get how much energy do you need to zap it with in order to get it to gas vaporize or evaporate? Or it can be per gram, whichever is more convenient. Okay, so the opposite of vaporization is condensation. So condensation looks like this, where I think I'll go ahead and put my G over here, and I'll put an arrow, and I'll put an L there. That is condensation. Okay, so actually we said energy is going to be released. Okay, and as it turns out, for the same substance, if you are evaporating 1 gram, you're going to release a certain amount of energy. And if you condense that 1 gram of gas back into a liquid, you're going to release that same amount of energy. Is that not cool or what? It makes sense. So for the same substance, basically, they are equal in magnitude but opposite in sign, we say. So the absolute value are equal. The problem is, and I have a slide to tell you, that basically you'll find these latent heats of condensation, but you won't find these latent heats of vaporization. So you have to make the switch if it's needed. For the same substance, whatever amount of energy is required, is required to vaporize it is equal to the amount of energy that's released as it condenses. That threw me off. So like I said, you'll usually find the delta H vaps, the latent heat of vaporization, but not of condensation. All right. The other two things, or the other phase change we're going to talk about, we're not going to talk about sublimation, I guess, is the whole melting freezing thing. So like I said, instead of delta H submelting, it's delta H subfusion. Melting and fusion mean the same thing. I don't know. Okay. So of course it's endothermic. Okay. So melting and fusion mean the same thing. I have to look that up. Now, that's not Latin. Somebody just decided to throw another term in there, I think. So, of course, the other thing, aside from melting, we need to talk about freezing. So melting and freezing are going the opposite directions, but they're the same two physical phases they're dealing with. So, the heat of freezing, okay, the latent heat of freezing, delta H sub freezing, energy is released. Okay, it's actually going to be the same magnitude as the latent heat of fusion, but opposite in sign. So we kind of have the same deal. Freezing and fusion are kind of the same deal as vaporization and condensation. Very good. But again, you're going to see the endothermic version. You're going to see the fusion, not the freezing. Okay. Okay. So here is a table that you might find helpful. The melting points, I'm going to show you in a minute why you would ever want to know the melting point temperature in a thermodynamic problem, like we're going to work here in a minute. But the melting point temperature is the transition temperature between a solid and a liquid. And then there's the latent heats of fusion in joules per gram and joules per mole. You could convert those back and forth if you had the molar mass of the substance. Then for those same elements, we have looking at the whole liquid-gas transition, okay? This is, again, is the endothermic version. If we wanted to know the latent heat of vaporization, okay, latent heat of condensation, we would basically take the same number and slap a negative sign in front of it. Compounds, same thing. So if you want to take a look, actually I inserted a new problem. I didn't work it out yet, but I brought my calculator. We're going to work kind of, we only have one problem until we're done with this part. But I want to work kind of a baby problem leading up to our water problem. So we're going to pick on benzene. So all this stuff about benzene, I wrote down a little note card so I could have it. So benzene, it melts at a chilly 5.48 degrees Celsius, okay? One of the things it's good to kind of find your way around chemistry problems is you see that it boils at 80 degrees Celsius. Room temperature is 25 degrees Celsius, 20 degrees Celsius, 21 degrees, 25 would be pretty warm. But my point is, can you see that normally benzene would be what, a liquid? Does that make sense? From the freezing point temperature, or freezing and melting point temperature, and the boiling point temperature. So we're going to use these numbers to do this problem right here. So you don't have this problem. It's an extra problem. Okay. So let's take a look at it regarding benzene. Now you have the slide, and I have the information for that line. So notice for this particular problem, and just kind of bear with me, I didn't have my little superscripts in, so this should be degrees, and, well, 80 I think will work. Consider holding liquid benzene right at its boiling point temperature. How much energy is required to take that liquid benzene and to vaporize it and zap it into gas if the mass of liquid you're trying to vaporize is 54.3 grams. So here's what the picture looks like. Here's my picture. Here's my liquid benzene. I'm going to zap it with a certain amount of energy, Q, and I'm going to call that Q of vaporization. Okay, and I'm going to go ahead and, if we were kind of going from left to right, what's it going to look like? Over here, it's going to look like a gas. Basically, that's what we have going on here. The mass doesn't change. The mass in both cases is that 54.3 grams of C6H6. All right, so basically, if you're trying to knock out the Q of vaporization is equal to the mass of the C6H6 times the latent heat, delta H, of VAP. And you have two choices on that table. you have the latent heat of vaporization in energy per gram and energy per mole, so we're gonna go with energy per gram. So if it looks simple, it kind of is. Maybe that's why I never usually have a problem like this. So Q of vaporization is the mass, which we said is 54.3 grams over 1. And then from that table, I am going to pick out, I got 127.4 kilojoules per gram. Kilojoules per gram for benzene. Does that look okay? I'm thinking so. And that's the answer. It's not that tricky. It's like a bounty hunter. Okay, so rounded to 3 sig figs times 127.4. Oops. Okay, so I got 1917.82. So rounded 3 sig figs. Let's leave it not in scientific notation. So I got 6920 kilojoules of energy is required. Okay. All right. So then I picked this one. It's benzene, and it says how much energy is released. So we should be starting to think, our Q is going to be negative, right? So in this case, we are dealing with, it's gas, and we're going to form liquid. It's condensing. Okay, energy is going to be released. And in this case, we know the amount, 34.6 moles of C6H6. And it's going to liquefy. Okay, so here, Q that is, I can do it this way. Q that's released, Q is COND, Q of condensation. We can calculate. I'm just going to go ahead and leave it as M for mass, but actually we're going to go with probably moles here. M for mass or amount of C6H6 times delta H of COND, that's condensation. Cool. So the thing is when we look at, oh, you guys let me use the wrong thing, didn't you? No wonder you're looking at me like, really, Mrs. Snipes? Okay, so up there, I used this. She really should have used 393. This one. Darn it. 393 joules per gram. Final answer. Does that look better? You people. Okay. So that changes this. I'm really not stalling, I promise. So 54.3 times 393. That's better. Wow. Again, 3 sig figs, I got 21300. And units would be, although I think joules, right? This is why I don't do things on the fly. Okay. So now my point was going to be, if we look over here on that far part of the chart, in order to know what the latent heat of condensation is, we need to turn our attention to the latent heat, or the delta H of vaporization. So we're going to go with moles instead of grams, and actually the delta H vaporization is, I got 30.7, I hope it's joules per mole. Okay, so therefore the delta H of condensation is equal to negative 30.7 joules per mole. Final answer. So bottom line, we can work this by simply taking the moles, which is 34.6 moles over 1, and then plugging in the delta H of condensation, negative 30.7 joules per mole. All right, 3 sig figs. Three 4.6 times 0.7. So I got 1060. And that would be units of joules. That's it. Okay. Oh, what did I forget? Negative sign. Final answer. Okay, we good with that? Okay. Energy released during condensation, energy required during evaporation. Was it kilojoules per mole? I must have wrote it down on my thing wrong. Is it 30.7 kilojoules per mole? Mm-hmm. Thank you. Let's see. Can I go back? I can. Okay, so I'm going to put a K, thanks, in front of this one. Very good. Very messy, but you get the idea. Is that better?
Yeah, I just can't finish it.
You can. Okay, so now on to your back to your notes. Okay. So remember when we were talking about the system and we only had 2 things in the system? I'm like, there's only 2 things in the system, and the system's isolated, so the change in thermal energy between the system and surroundings is 0. Well, now we have several things in the system going on. So it doesn't look too bad because it's not very wordy. I don't need to be dramatic about it, but it's been a long week. So basically what we're doing out is starting with solid ice, okay, at a temperature clearly below freezing. And we want to ultimately get those water molecules. They're going to go from a solid to a liquid, and we're going to jack them up to a gas to a temperature that's above the boiling point temperature. So we have a few things going on here. We have transition changes, like physical phase changes, and we also have the thing just kind of heating up as we go. So we have to think of it kind of stepwise. And this is what it looks like. It actually ends up being 5 steps, 5 different steps. So if we think of that very cold ice, the first step is going to be bringing that very cold ice up to the melting point temperature. So that's going to be our first Q. And I say it in my notes later, but actually in order to do that, we're going to say change in thermal energy, Q of the ice. I'll put ice warming. The more descriptive you can be in your subscripts, the better off you are, is equal to the mass of the ice that's warming, m c sub p delta t, basically. Okay, so that's what we're going to do to get it up to that melting point temperature. Then once it's at the melting point temperature, we need to transition it from a solid to a liquid. And in my notes, what you're going to see is at that point, we're going to use the Q of melting is equal to the mass that you're melting, which is that 50 grams, and then times the delta H of fusion. I'm waiting for screen. Then, once you get it all liquefied, then you're going to go ahead and take the liquid up to the boiling point temperature. It's a liquid all the way. And again, you are going to use the Q is equal to m c sub p delta t. Still waiting on screen. So I would write it on here, but this is not playing along. That's 3 of the 5. The 4th is after you have it right at the boiling point temperature, then you're ready to take the liquid and vaporize it all. have it go from a liquid to a gas. And we know that we're going to use the latent heat of vaporization for that. Then once you have it all a gas, then you're ready, which is 100 degrees Celsius, then you're ready to take it to your final temperature, which was it 200 degrees Celsius? Crazy. So it's all vapor, and you can take that gas from 100 degrees Celsius to 200 degrees Celsius. So it ends up being like 5 steps. And I still have a black screen. That's okay. Okay, oops, now nothing's open. So kind of like we've been talking about, we can actually think of it in terms of individual changes in thermal energy, all added together to make a change in thermal energy of interest. So actually, what are we after this time? We're not after we are after the overall change in thermal energy associated with the process, which is these various steps. Add them up. So this actually, you can look at it two ways. You could almost kind of look along the x-axis as time if you're just kind of pumping it with constant energy. But instead of time necessarily, it is actually how much energy are you putting in. Okay, so along the, I said x, I meant y. X, yeah, x-axis. Along the y-axis is temperature. Okay, so the y-axis is tracking those important temperatures that your phase is going to change. For instance, okay, it's going to start as a solid. Actually, I think I have belts here. It's going to start as a solid, and it's going to, at 0 degrees Celsius, it's going to liquefy. But we need to talk about how much energy is required to take that solid from -50 up to 0 degrees Celsius. Okay, so that's Q of ice cooling. Then what it's going to do is basically hold this temperature, but we're going to keep pumping energy into it, and we're going to melt it. Okay, so it's going to stay at 0 degrees Celsius, and it's going to melt. And we're going to call that Q of melting. Then it's going to be a liquid, and then we're going to keep pumping energy into it, and it's actually going to heat up from 0 Celsius to 100 Celsius as a liquid, up to the boiling point temperature. And that's what we're going to call Q of heat or warming the liquid. That's what I would call it, whatever it said there. And then once it's a liquid, we're going to pump it with, you can kind of see the length of it is basically how much energy it requires. So actually right up here, you can clearly see where vaporization takes a lot more energy. So it's going to hold that 100 degrees Celsius, and it's going to go from a liquid to a gas. And how much energy is required there? That would be the Q of vaporization. And then it's a gas over there. And then when it's a gas, we need to take it from 100 degrees Celsius to 200 degrees Celsius. Okay? And that would be the Q of heating the gas. So basically here you have a Q of ice warming right here, and here you have the Q of melting, and here you have the Q of water warming, liquid water warming. It's funny how when we say water, we assume it's in its liquid state. That's this right here, and here you have the Q of vaporization, and here you have the Q of gas warming. However descriptive or not descriptive you want to make those Q values. You add them all together, and that's how much energy we pumped into it. So let's do each of the 5 parts and add them together and call it a day. Okay. So the first one was to take the solid from an initial temperature of -50 to a final temperature of the melting point temperature, which is 0. The delta T is 50 degrees Celsius. Remember, you're supposed to memorize the specific heat of liquid water, which is 4.184 joules. But for solid water, it's 2.06 joules per gram degree Celsius. So we do all that. We round it to 3 significant figures. 500 grams times 2.06 joules per gram degree Celsius times the delta T is 50 degrees Celsius. Round it to 3 sig figs. Oh, before we do that, let's go ahead and convert it to kilojoules. So 1 kilojoule over 1,000 joules. Now we can give ourselves 3 significant figures. 3 significant figures, 51.5 kilojoules of energy required just to take that ice from negative 50 to 0 degrees Celsius. That's the Q of ice warm. Q number 2, okay, to go ahead and melt that ice, we're going to basically want energy per gram. Okay, so the latent heat of fusion is 333 joules per gram. So we'll take our mass of the ice, 500 grams, so 3 sig figs, times 333 joules per gram. And let's go ahead and get it into kilojoules, times 1 kilojoule for 1 kilojoule for 1,000 grams. And 3 significant figures. Okay, looks like 167 kilojoules of energy is required. Then it's all liquid, and we're ready to go ahead and jack it up from its melting point temperature to its boiling point temperature. So in this case, we still have 500 grams of water, so 500 with 3 sig figs grams, times the specific heat of liquid water, 4.184 joules per gram degrees Celsius. The change in temperature is final minus initial, so it's 100 degrees Celsius minus 0 degrees Celsius. So it's 100 degrees Celsius is our delta T. Get it in units of kilojoules, so 1 kilojoule over 1,000 joules. And round to 3 significant figures. And we have 209 kilojoules of energy. We're required to, what are we doing here? We're required to get our liquid from 0 to 100 degrees Celsius. Then once it's at the boiling point temperature, we're ready to zap it and to vaporize it. So we go back to this equation. So to come up with the Q of vaporization, we're going to take the mass of the liquid water to vaporize, 500 grams with 3 sig figs, times the latent heat of vaporization, which is a whopping 2.26 times 10 to the third joules, or 2260, right? Joules per gram. And get that into kilojoules, 1 kilojoule over 1,000 joules. 3 significant figures. That's going to be 1.13 times 10 to the third kilojoules, or 1,130 kilojoules. Phew. So now we all have it. We have it in its vapor state at 100 degrees Celsius. Now we're ready to jack it up from 100 degrees Celsius to 200 degrees Celsius. So we need to go back to this Q is equal to MC sub P delta T. So for our last Q, it's going to be the mass, which is still 500 grams. The specific heat of water vapor is 2.03 joules per gram degree Celsius. Our delta T from going from our final temperature is 200, our initial temperature is 100, so our delta T is 100 degrees Celsius. Get it from joules into kilojoules. We put 1 kilojoule over 1,000 joules, rounding it to 3 significant figures. We get 102 kilojoules. And now we're ready to add them all up. So this is what we came up with for each one of those Qs. So we don't, again, do a lot of adding in chemistry, not nearly as much as we do multiplication and division. I always say if you're adding, you round to fewest number of decimals, and you'd be like, well, what is the fewest number of decimals? And as it turns out, it's not decimals per se, but it is places. So actually, the uncertainty begins in the tens place. I know that sounds weird, but the tens. So that's how we're going to have to round it. So this number, of course, expanded is, oops, sorry, go back, is 1660 kilojoules. So we round according to the nearest tens place. There you go. Yay! So there's where you might say, well, Mrs. Snyder, will you have one like this on the test? And I'd be like, I don't know, the test isn't made out yet. So again, this is kind of what we did. This is a summary of what we did. So let's take a look at the problems and let me know if you see anything about the problems. But there we are. Definitely have the picture thing going here. Okay, so this one, I basically, and I've seen some of you guys do this, kind of started backwards. If you read this a few times, it makes sense for me to start backwards. Basically, there it says that that you have 3.50 moles of liquid water, and you want to raise it up, the delta T 50 degrees Celsius. What is the energy you need to pump in there? Because then it says what mass of ice can, what mass of ice can be melted with that same energy that was required to raise the temperature. I know, you're like, really? Could you not even make this any harder? The questions sometimes are the hard part. So I've looked at it a few times, and you'll have to look at it when you go to do it, but trust me. So of course we can get the amount of energy required to make this temperature change by using Q is equal to MC sub P delta T. And I think that there's a specific heat somewhere in energy per mole per degree Celsius, but if you need to go from moles, use its molar mass to go to mass to plug in here, you can. But anyway, so then it says if you take that energy and instead now you apply it to melting ice, how many grams of ice can you melt? So here's my little hint. Anytime you see, in this class anyway, like a triangle, 3 dots, that means therefore. So what the problem is saying is that the Q that you're going to apply to melting is equal to the Q that you applied to heating the water. So in that case then, the Q of the melting is the moles of water that would be melted times the heat of fusion. And then of course that will give you moles, and you need to go from moles to grams. So that's my hint for that one. For this one, we're passing steam, gaseous water through liquid water. It gives you the mass of the steam that we want to pass. It gives you the initial temperature of the steam. For the water we're passing it through, it gives you the mass of the water, and it gives you the initial temperature of the water, but it does not give you the final temperature of the water. In this case, it wants you to tell them what the final temperature of the water will be. So here's the catch. There's actually 3 things going on here. Because that steam needs to condense, okay, so there will be a Q associated with the condensation. It will be negative. Energy will be released, okay? And also the steam needs to, that little 5 grams of steam, it needs to condense from its initial temperature of 100 degrees Celsius to some final temperature, which is the same final temperature as your water. So that's the hidden term a little bit. Your third term, obviously, is the Q associated with the water changing temperatures. Okay, so the water will heat up to a final temperature. That little 5 grams of condensate will cool down to that same final temperature. Now in this case, we go back to it is an insulated container, so there is no, the Q of the system is equal to 0. So basically, the only thing you don't know is, the only thing you don't know is the final temperature. But it's the same final temperature for both. That's my hint for that one. 31. Actually, 31 and 32 go together. They both have the stainless steel ball, the same mass of the stainless steel ball, the specific heat of the stainless steel is given. The initial temperature of the stainless steel is a whopping 525 degrees Celsius. You're going to douse that stainless steel ball, in this case, into water. They give the volume of the water. They give the initial and the final temperature of the water. Oh, wait. In red here it says, if you read the problem statement, basically the water is going to be heated, going to have more than enough heat to begin boiling. It's going to go from its initial temperature of 28.5 up to 100 degrees Celsius and begin vaporization. Okay, so your final temperature is 100 degrees Celsius. The final temperature of your stainless steel ball, is also 100 degrees Celsius. So again, you have 3 things going on. I think 3 things. I know, you're like, really? And come up with whatever subscripts work for you. But we definitely have the stainless steel ball cooling down, okay, to 100 degrees Celsius. We have the water heating up to 100 degrees Celsius, and then we have a certain amount of water vaporizing. So that's your third term. Your question here is, what is the mass? Yeah, what mass of water will vaporize? Do I have any more hints there? Here's where I say, by the way, the final temperature of the stainless steel ball is the boiling point temperature of water, 100 degrees Celsius. So basically, you have everything except for the mass of the water that vaporizes. Yep. One more. Okay, in this case, you're going to take that same stainless steel ball, thank goodness for copy paste, and you're going to put it on solid ice. And your question is, how much of that ice will you melt? It's kind of a fun question. So in this case, as far as I can tell, you only have 2 things going on. Phew. Okay. You have the stainless steel ball cooling down from 525 to the melting point temperature of water, which is 0. Okay. And then you have a certain mass of water that is melting. So the only thing you don't know is the mass of the water that would melt. So some of these, for chemistry problems, don't feel, especially, I guess maybe even Chem 2, if you need to go looking for like heats of vaporization or specific heats or something like that, don't say, well, am I doing the problem right? Well, probably you just need to go look for them. Okay? So, but you should have everything in Petrucci, because these are Petrucci questions that you need. Okay? All right, I'll post these. Remember, this is the end of thermodynamics. And then we're on to happy things. On Monday, we'll start Unit 4. But don't forget this stuff, because you got to test over it.